Okay, hello back again. We've got 5 speakers in the afternoon. Daniel Richards and Martin Amos, they're from Dalton Research Institute at Manchester Metropolitan University, are going to be first, followed by Andreas Studart, that came over from Switzerland, ETH Department of Complex Materials. And then Andy Payne and Panagiotis. Panagiotis would be presented because Andy couldn't make it, from Harvard GSD. And then a short break, followed by Lambros Malafouris from University of Oxford and Rachel Armstrong from the University of Newcastle. So the first to present is Daniel and Martin. Thank you.
Hello. So firstly, thank you for the invitation. It's an honor to be here. So I think that the presentation today is in a sort of good time because the discussion that followed, it was before lunch, was really interesting and sort of relevant. So what I want to do is try and talk about some of the computational challenges. So my background is in architecture, but I'm now working as a postdoc research associate in the Biological and Sensory Computation Group, which is led by Martin. So as a group, we're sort of broadly interested in biological systems and how they're constructed, how they operate, and some of the sort of amazing properties that they have. So through computational modeling, we try to build our own systems that have similar properties. And so I'm particularly interested in how we can leverage computation and build entirely new types of structures with additive manufacturing. And so that's what I want to talk about today. So I'm going to talk about some of our work we've been doing with volumetric modeling. So we have some new ways of manipulating material and geometry within voxel-based systems. And so, first of all, I want to highlight 3 of the big opportunities that we see for multi-materiality in general. I'm then going to talk about this big challenge that we see in computation, which is about the representation. And so this is actually, it talks about the sort of boundary representation with the voxels. And then I'm going to present our approach where we're using evolvable volumetric gradient patterns. So this is really moving from sort of vector-based graphics to, from raster-based graphics to vector-based graphics. And finally, I'm going to demo some of the work that we've been doing. Okay, so firstly, one of the big opportunities we think is high performance. Nature just builds these incredible material structures. It somehow manages to take weak materials and combine them in ways that make them strong. And this is done by manipulating the microstructures. So we can see that maybe we can start to do this. Maybe we can take recyclable materials, weak recyclable materials that we have lots of, and combine them in ways that make them strong, high-performance structures. So you can imagine sort of next-generation form finding, almost like earthquake-resistant buildings in the future, sort of light skyscrapers, perhaps. But there's other opportunities as well, and this is about really combining different materials together to create actual behaviors. And so I'm sure you've seen things like Skylar Tibbetts, 4D printing, self-assembling materials, and sort of morphable structures as well. There's lots of work in aerospace about structures which can bend, sort of exotic compliant mechanisms, and perhaps even in the future, towards integrating living materials. Another thing we see, this opportunity for new aesthetics and new types of formal possibilities. Tom Wiscomb's talked about this highly integrated multifunctional features and sort of graded compositions. Elaborate surface textures, such as the things by Neri Oxman. And we can almost imagine designs which start to celebrate some of these machining logics, these sort of additive manufacturing processes, and perhaps even towards this sort of Gothic brutalism type style. Okay, so before we can get to that, there's some serious technical challenges, as discussed before in the discussion. In terms of the fabrication kit, we need to be able to increase the speed of these things. 700 hours is still quite a long time. We need to be able to increase the build size. Again, another big issue. We need to be able to increase the resolution and the quality. Again, these are things we all know. We need to be able to expand the palette of materials. And we need to be able to resolve how these things start to bond to each other or are assembled in different ways. In terms of the simulation side of it, we have big issues in terms of how we accurately sort of simulate these materials and these behaviors, especially when it's multiple materials together. And again, we need to be able to do this in times that are not excessively long. But we also think there's major design problems. If these are the sort of technical problems which there's engineers working on, there are serious design problems, and these are our problems. These are the ones we've actually got to address. And so the first one is about moving from sort of boundary representations to voxel-based models. And it's really about material integration, as discussed before. But we think there's a second problem, and this is perhaps less discussed and maybe less understood, but it becomes increasingly important as we start to move towards multi-materiality. And that's this idea of scalability. How do we actually start to control some of these structures? They're really, really complex objects. So, for example, imagine we'd start to look at these sort of Heinz-Isler type structures, these shell structures, and we wanted to be able to create the next generation of these with multi-material properties. Perhaps we could consider how we could change the geometry, but also change the material all the way through. The problem here is that these structures just have so much information, and they have so many degrees of freedom, and they have so many different combinations, possible combinations. Okay, so one of the big problems that we see is how do we actually start to discover good combinations of materials in this space? But before that, it's really, how do we actually even encode this type of structure? Okay, so the most obvious way we could do this is we could look at direct encoding. So here we would have a sort of variable parameter which would stick onto every one of these voxels or pixels, and that sort of works quite well if you have a small amount of voxels, or if you're working on a reasonably simple or well-understood design problem like sort of topology optimization, where we have good mathematical treatments. However, if you want to do something more elaborate, like some of the stuff that Kostas was talking about at the start, or perhaps even like that shell structure, having these sort of really high-performance structures, then we need different ways, different algorithms for sort of searching the space. Now, evolutionary algorithms are quite good at this, and they're a good sort of option. However, you start to incur this type of problem. And the problem is that as you increase the number of parameters you have, you also increase the amount of time it takes to solve something. And this is really problematic for multi-material design, because all of the structures we want to be able to design are probably in this red area, which means that we can't really access them with the algorithms that we have. And so our research for the last sort of 2 years has really been about trying to change this graph into this graph. How do we actually access that space? How do we encode our designs in ways that have few number of parameters, but allow us to explore this vast space of form and discover good material properties? Okay, so we've established that direct encodings are not that useful in this area. And this is really the sort of key idea. This is the key slide that you need to remember. Okay, so we can imagine a simple gradient-based encoding instead. And this is something that we're all probably familiar with. You could create a grasshopper definition that did this. We could start off with a grid of material. We could put a coordinate system on this, and we could take the inputs from the x and the y, feed them through a really simple function, and they would spit out a color. So that function here is just a simple addition. So what we've been working on is a different type of approach, which is called a CPPN, which stands for Compositional Pattern Producing Network. And it's basically the same idea, but slightly more complicated. The idea is that we feed in the coordinates, we rattle them through a slightly more complicated function that has weighted connections, and the nodes have things like sine and cosine and Gaussian. But essentially, it's the same thing. But the really important thing about this is that we have an algorithm where we can evolve these CPPNs from scratch, which means that we actually move from almost this sort of raster image, which is static and it's fixed, to evolvable vector graphics for at least 2 dimensions. And this is a really big jump. And so I need to make a switch. I stupidly used Windows media files. Okay. So the nice thing about this is that once we have these CPPNs, we can actually extract those connection weights, and we can manipulate these things in real time. And so the thing to note here is that these complex patterns actually have quite a compact encoding. So I'll play that again. They have a compact encoding, and note that if we added more pixels to this, we don't need more parameters to encode this. This is a functional representation. So it's fundamentally different from this sort of bitmap representation from before, this sort of direct encoding. Okay. Okay. So with this, we can create some nice 2D images really quickly. And the really nice thing about this is that the patterns that come out of this have 3 really important properties. First of all, they are scalable. Like I said, they have this compact encoding. Secondly, we get these sort of nice symmetries and regularities, and these are due to the periodic functions that we have in the CPPN, like the sort of cosine. And we also get this property of infinite resolution, which means that we can zoom into these things forever and just keep on querying the CPPN. So we have sort of unpixelatable images here. Again, potentially useful. And so moving on to the work that we've been doing at the moment. So what we can do is we can actually replace the X and the Y coordinate system and use NURB space geometry. So we can take a surface in Rhino, bring it in and key on the UV coordinate system, and we can create patterns along surfaces. So this is quite nice, and as you can see on the side, as different parameters make big changes, and some parameter changes make very small changes. And this makes them, good for evolution, which we can actually optimize these quite well. And we've shown this through a few other studies. So it's a bit like playing with a sort of automatically generated grasshopper definition, I guess. Okay, but we can also use these to manipulate the surface, not just add color. We can take all of the points and we can query them and we can extrude them along their normal, for example. And then because we have this evolutionary algorithm which underpins it all, we can start to evolve surfaces that have good structure. So we can use sort of simple FEA things, software, and we can assign boundary conditions, assign loads, and we can optimize for specific mechanical properties of these surfaces. And obviously we can fabricate these quite easily. And so these 4 that you can see at the bottom here is sort of really me playing around a little bit. I've set up this almost like a sort of Heinz-Isler type surface. I've assigned some boundary conditions. I've assigned a load on the top. I've allowed these things to evolve for a little while, and then I've stopped it. I've extracted those parameters. I've had a little bit of a play, started evolution again, and sort of had a bit of a play really. So these are sort of speculative designs that are informed by design and optimization. Okay, so now it starts to get really exciting when we start to introduce multimateriality, because these things also work in 3D. So for example, if we use the U and the V coordinates of these NURB surfaces, but we also have a sort of a Z coordinate which is relative to the normal of the surface, if that makes sense, then we can start to create shell structures which have a thickness, and we can manipulate all of the sort of voxels within that surface, within that sort of volume, sorry. So what you can see here is simple XYZ geometries where we've used our CPPNs to create sort of random patterns to show really. And so as this CPPN shows, we have an output which says, are we going to place a voxel there or not? And if we are going to place a voxel, what's the material property of that going to be? And so this work is sort of still in process, but we're hoping to be able to create some nice multi-material structures in the near future and be able to optimize these for certain mechanical properties. Okay, more videos. Sorry about that. Okay, so this is an example of a 3D CPPN where we are extracting the parameters. We can have a little bit of a play, but we can also change the resolution because this is sort of vector-based object now. We have lots of control. So what we're really doing is we're encoding the logic for this thing. We're not encoding the object anymore, we're encoding the logic. That's enough. Okay. So this, we can also do this with, it doesn't necessarily have to be these sort of cube-like voxels which we throw over surfaces. We have another method where we can create lattice structures within surfaces, again using the same method, using a U and a V and an extruded Z coordinate system. And we've created, we've sort of developed a system which is called CPPN Neat with a dynamic substrate, which allows us to optimize lattice structures within these as well. And so as you can see by this sort of dynamic image, this sort of GIF, that we don't necessarily have to optimize just for sort of static behavior anymore. We could actually start to create compliant mechanisms, sort of morphable structures, and there's lots of exciting opportunities when it gets to this stage. Again, this work's still in progress, and so we'll be working on this. So, in summary, we've created this sort of nice, scalable encoding for multi-material design. Or we haven't created it, we've been developing it. It's the actual algorithm was developed by Ken Stanley. We've been able to present some nice sort of complex shell designs, and there's lots of opportunities here. And we can control material compositions in ways that we couldn't beforehand. But there's some nice properties to this. First of all, we have this sort of very powerful algorithm under the hood, which is neat, so we can optimize these. Evolutionary algorithms are really well suited for distributed computation, so we can actually throw these things up onto the cloud potentially, and we can evolve really complex things. And this is where I think it starts to become exciting as well, that we can start to fabricate structures which are too complex to actually simulate on the computer. So as Francis talked about before, there's this important process where we take our three-dimensional models and we slice them up. So if you see this two-dimensional image on the far right, we can actually create our slices from the CPPN information. So we can query each slice, which means that we can massively extend this, to the biggest resolution that we can actually handle. And we can create all of those slices, and the final object could be much more complex than we could actually simulate on the computer. So this is interesting as well. And so finally, the thing to point out is that we're not limited to sort of NURB space geometry. We can do this in three-dimensional space. We can So we can start to play with these things more speculatively in three-dimensional space. There's lots of opportunities for sort of generative design. Again, we maintain all of these properties that I've talked about, sort of scalability, the regularities, and the sort of infinite resolution. And we can start to play with these things in terms of, with physics systems and all sorts of things. So I guess the takeaway point is that once we start to move towards multi-material design, we start to create objects which are truly complex. And therefore, we need representations which can handle this. And CPPNs are a good option here. And so the tools and techniques that we've presented seem to be one good route towards being able to create multi-material design as we move forward. And that is the end. Thank you.
Okay, so good afternoon. My name is André Studert, and I'm a material scientist, not an architect. And I'm at ETH Zurich, and we're working mostly on composite materials. But first, I want to thank Kostas very much for the opportunity to be here in this really interesting meeting. So I'm going to start with a slide that addresses the very interesting point made this morning about the idea of having a catalog of materials from which architects could draw properties and information in order to fill in an algorithm or a software that would help them design materials. So the reason why I start with this is to make the point that actually, if you do that, and if you think about all possible sources of materials available that are processed through made technologies, you can basically have the whole periodic table, which is very good, of course. But it's also interesting to see how this is done in nature by living organisms. And if you look at the materials in terms of chemical elements that they use, this is a lot more restricted in terms of chemistry. And why is that interesting? That's really interesting when you think about energy efficiency, sustainability, biocompatibility, and so on. Why? Because nature had to live with this very narrow selection of chemicals in order to be energetically efficient, sustainable, biocompatible, and so on. So how does nature do that? It actually does that by taking this narrow selection of chemical building blocks and then arranging them in a very special way, as we heard already in the previous talk. And this leads to really interesting structures. We already heard about the seashells, the inner part of which is nacre. We also have amazing examples of microstructured composites like the tooth, the tendon to bone connection, which would be a region of very high stress concentrations, and yet it's very resistant to fatigue. But it's not only about mechanical properties, but there are also very interesting kinds of shape changes that are possible by microstructuring these materials. And here it's important to note that this shape change happens in the absence of any cellular control. So this is dead material, yet it's able to change in this dynamic fashion. So what's really unique about these materials is that they really have amazing microstructures, and that's what enables them to make something weak into something very strong or functional. And here are some examples of the types of microstructures that you see when you take these biological composites in a microscope. So you see, for example, in this particular slide, I highlight two things. One is the ability to control the orientation of building blocks, be it a fiber or a platelet, for example. You see that in nacre, vertical alignment up here, horizontal alignment here, the same kind of vertical and horizontal alignment in the tooth, and also in these plant systems. So actually in each one, if you look at the seed pod, in each one of these halves of the seed pod, you see a bilayer with cellulose fibrils oriented in a very particular way to generate this shape change. And here's another example where you rather have a gradient well, you have a combination of a gradient and orientational control as you go from the soft tendon to hard bone. So this slide quantifies a little more the effect of this microstructuring that the living organisms rely on. So here we are looking at the toughness as a function of the stiffness or the elastic modulus of a range of different biological materials. And I want to highlight the comparison here between, so to speak, unstructured calcium carbonate and the seashell. And the point here is that the seashell is made out of 95% of calcium carbonate. So by just looking at a catalog, you would not be able to distinguish between the material of a mollusk shell and the material of just man-made calcium carbonate, so to speak. But the way these materials are structured allows them to increase the toughness by 2 orders of magnitude. So it's really a very significant effect, this of structuring. Okay, so one other important aspect is that it's not always that we want to mimic one-to-one what's available in nature. First, because we can, in some applications, actually benefit from the wider range of chemicals that we have in man-made technologies. On the other hand, the boundary conditions in nature might be very different from engineering. So what we would really like to copy from nature is not the structure itself, but the design concept or the physical or mechanical principles behind these structures. So there's a lot of work going on in the scientific community trying to understand what are these design concepts for many different biological composites. And here I just show a compilation of some of these design concepts. We are actually working on all of them, but today I'm going to focus on just 2 of these concepts. One is in controlling the orientation of building blocks and how to exploit these in order to have these kinds of shape changes in dead material. However, it's important also to remember that all these beautiful microstructures are all made via cell-mediated processes. So you need living organisms to make all this. So the big question in our field is how can one actually make this synthetically? So how can one make this using not the slow processes that nature uses, nor the complicated cell machinery, but in a more engineering approach. So today I'm going to focus on these self-shaping composites. I already alluded to the example of these seed pods, but there are many other interesting examples like these little hairs on top of a wheat grain. They're the example of pine cones that are close if you put them in water from an initial dry state, and of these ice plant seeds which open as soon as there's one single droplet of water. So the design concept behind all these structures is very, very simple, and that's illustrated in this cartoon. What you actually have is a certain reinforcement. In nature, it's mostly cellulose fibers. Here I'm representing it as platelets. And this reinforcement is oriented in one particular direction, and then you have a continuous matrix around it, which is responsive. In this very simple example, it just expands, takes up water, and swells. But because this matrix is mechanically constrained by the reinforcement, swelling will happen preferentially 90 degrees to the direction of the reinforcement, but not in line with the reinforcement. And that is the very simple idea behind many of these shape-changing structures in nature. If you take the pine cone, for example, it's in its dry state, it's open like this. If you put it in water, it closes up. Now, if you look at each one of these scales, you will actually be able to represent it as a bilayer, where on the top layer, cells lay down these cellulose fibrils in a horizontal fashion, in the bottom layer in a vertical fashion, so that if we swell now the green matrix, which in this case is hemicellulose, there will be more swelling of the bottom layer as compared to the top layer, so the natural tendency is that the material bends, just like a metallic thermostat. The exact same idea, though in a slightly different configuration, is seen in these little hairs of the wheat-on structure. And here we have, again, this bilayer in which on one of these valves. But this time, well, again here we have the fibers orthogonal to one another, but this time you have them tilted by 45 degrees with respect to the long axis of the system. And therefore you don't have pure bending, but you rather confuse the system and lead to this twisting as the minimum energy configuration. So what I'm going to show you today is basically how we can, in an engineering approach, try to replicate this design concept. So I divided the talk in 2 parts. First, I'll tell you about a technology we've developed to align anisotropic particles in a fluid and then afterwards consolidate this fluid so that we keep this alignment. And second, how we can use this to achieve these self-shaping properties. So the technology we use to align these anisotropic particles is very simple. It's based on the application of an external magnetic field. And I usually illustrate this concept using this macroscopic example. If you take metallic washers and you put them on top of a magnet, you will see something like this. They will all orient parallel to the direction of the applied magnetic field, which in this case is coming out of the screen. So it is this very simple concept that we use in this technology. One problem is that it's not always that you will have reinforcing particles which are magnetic. The metallic washers are magnetic themselves. So in that case, you have to come up with a trick to make non-magnetic fibers or platelets responsive to a magnetic field. We do that by, there are two means to do this. One is by adding magnetic nanoparticles into the fluid. So imagine now these particles are suspended in the fluid, and now you add to this continuous phase the magnetic particles, or you absorb these magnetic particles on the surface of your fibers. And in both cases, what you're doing is creating a mismatch in magnetic properties between the dispersed phase and the continuous phase. So this is how we do it in practice. This is one of the types of reinforcements we use. These are ceramic, very stiff platelets of aluminum oxide, about 10 micrometers in the long axis and 300 nanometers in thickness. And now we coat them with iron oxide nanoparticles, so basically rust nanoparticles. So now I'm going to do the same experiment I did at the macroscopic level, but now under a microscope, looking at each one of these tiny microplatelets with the iron oxide coating. So first, they're relatively heavy. They're 10 microns, and aluminum oxide is quite dense. So they all sit in a horizontal fashion on the glass slide, but now I'm going to apply a magnetic field out of the screen again. And you'll see that as soon as the field is on, they jump out of the glass slide, very nicely responsive. And if we turn off the field, you'll see that they all get back because of gravity. So this works very nicely. But what was really a surprise to us was how low were the magnetic fields needed for such an effect. So we typically use tens of millitesla. So just to give you a feeling for it, this is the kind of magnetic field you get from the magnetic stripe of your credit card. Very, very low fields. And we went on to study this, and we realized that we're actually in a sweet spot in terms of particle size. Why is that? Here we look at the field required for alignment as a function of the size of your platelets. If you're very small, and that would be the range, for example, of carbon nanotubes that were mentioned this morning, then these particles are very Brownian. They're thermally very active, and therefore you need very high fields for alignment. If they're very big, and now you think about aggregates and very large particles, again you need very high fields because gravity plays a dominant role there. But there's a sweet spot here in between for particles in between, say, 1 and 50 microns, where it's extremely easy to align them. So now we have the ability to align particles in a fluid. All we have to do to get a composite is to transform this fluid. So imagine now a polymer melt or a monomer that you polymerize, to transform this fluid in a solid. So here's an example of one of our first approaches to do that. If we turn the magnetic field on out of the plane, you'll see that and then we consolidate the fluid, you see that we can nicely have these, the orientation that we got through the magnetic field. So in this case, an out-of-plane orientation as opposed to a horizontal orientation if the field is off. So one problem if you work with platelets is that you see them all sticking out, but if you use a static magnetic field like this, you don't get control over the second axis of orientation, and that limits the maximum concentration of platelets you can get. So to solve this problem, you can actually rotate the magnetic fields to force them to align into the plane of the rotating field. And here are some of the ways. These are all proof of concept experiments at very small scales, but in principle, there's nothing that hinders this from being applied in bigger structures. So we can do this on a little larger samples to measure the mechanical properties. We can do this under a microscope to study this alignment effect. Here's an example, again, of the little microplatelets, and now I'll apply a magnetic field in this direction, and you'll see that some of them align right away, but then I'll start, and some start rolling, and then I'll start increasing the speed of this rotating magnetic field, and you'll see that at a critical frequency, critical speed, all of them will align in this biaxial fashion, which allows us to really control in 2 dimensions the orientation of these platelets. So you can model all these and come up with an expression that tells you what is this velocity of the rotating field in order to achieve this alignment. So I won't go into the details here, but that's a very important quantification needed for the actual realization of the alignment. And here's an example of an unusual orientation, which is an out-of-plane orientation that you would not get by, for example, just applying shear to the system, that we are able to achieve using this technology. And you can imagine many other possibilities using the rotating field, static field, field gradients, combinations of responsive with non-responsive platelets, and so on. And here are some real microstructures that we've been able to realize using this approach. So now the question is, can we exploit it to make self-shaping composites? So here, I've told you already that the design concept behind this self-shaping effect is to align platelets or fibers in a given direction. And since we know how to do that, all we have to do here is basically to use this approach in bilayers. So here would be a first layer of your material, here would be a second layer, and in each one of the layers you have an orthogonal orientation of these platelets. And now if we just cut it and have a polymer matrix which is responsive to an external stimulus, we should be able to see these effects. And indeed, that's what we see if we take a bilayer and we cut it at what we call a zero cutting angle, because it forms a 0-degree angle with the bottom layer. If you do that and put it in water, you see that it nicely replicates this bending effect. However, this is rather easy to do with metallic bilayers. What is more interesting is actually this twisting effect. And here, for us, would be very easy to achieve because you can take the same bilayer but now cut at a 45-degree angle in order to reproduce this design. And if you do that, you see that you can nicely, and put them in water, you see that they nicely reproduce the shape change that we program through the fiber architecture. And you can then go all the way from pure bending to pure twisting with mixes of the two, with change the chirality depending on the angle, relative angle of the two, and that provides a wider design space for these self-shaping structures. The other interesting thing is that we can pick polymer matrices which are responsive to more than one stimulus. For example, this one would be responsive to water uptake and temperature, so that if you first increase the temperature, it twists in one direction, and then if you cool it down again and let it swell, it would twist in the other direction. And you can repeat this as much as 20 times, and it will always do it reproducibly. Of course, now if we talk about programming the shape change, you also have to connect initial parameters of your structure, like the relative thickness of these layers, or the cutting angle, with the final structure or geometry that you get. In the case of bending structures, this would be the radius of curvature. In the case of mixed shape change, you would have the radius and the pitch. And I won't go into details, but we are able to nicely predict these final geometrical parameters based on initial properties of your composite. The other possibility here is that you can program different regions of the material to undergo different shape change. So here we program this stripe this part to twist, this to bend to the left, this to bend to the right. And if you eventually put them in mortar, you see that they will react as we've programmed. So this brings me to the summary. I told you about technology that we've developed where we use magnetic fields in order to control the orientation of reinforcing particles, first in a fluid. And we had this surprising effect or observation that it's extremely easy to align these particles as long as you choose particles with the right size. And then I told you about how one can exploit these to make a wide range of different microstructures that are not possible with today's long fiber composite technologies. And then I gave this example where we've used this ability to align platelets in order to achieve such a self-shaping effect, which can be bending, pure twisting, and combinations of the two. And what's really important here is that, of course, you do have materials, synthetic materials that are also shape-changing, like metallic alloys and other polymers. But again, these are specific to a narrow selection of materials. If you think of metallic alloys, you have, for example, nickel titanium, which has one specific phase transformation that at the atomic level that allows for this shape memory effect. And with polymers, the same thing. You always need polymers with a specific glass transition temperature. And here, you're not limited at all. You can use any type of fiber, which is sustainable, energy efficient, bioresorbable, and so on, and any type of matrix as long as it's responsive to an external stimulus. So that brings me back to the very first slide where another possibility in terms of materials design is not only to pick one from the existing catalog, but take those which are interesting from other aspects and microstructure them to get interesting functionalities like this self-shaping one. So with that, I want to conclude and thank all those who really did all the work in the lab. For the first part, this was Randy Erb, a former postdoc of mine, with Rafael Libanori, former PhD student. And in the second part, we had also the contribution of my former PhD student, Jonathan Zander. There were also undergrad students involved, and I thank also for the funding and the opportunity to be here. Thank you.
Hello, everybody, and I would like to thank Kostas for organizing this great event. I'm here to present a software developed as part of our research on multi-material 3D printing and its applications in design. My name is Panagiotis Michalatos. I'm an assistant professor of architecture in Harvard GST, and this project has been developed in collaboration with Andrew Payne, who is a DDES graduate from Harvard, and he's now working for CASE. So as you probably already heard, and I think there was a lot of resonances with previous presentations here, as designers, we work always through representations. And especially software tools as representations of design, it poses certain restrictions into our thought process and design process. There are two levels at which software tools affect or construct a designer's subjectivity. One is the underlying data structure, which is basically also determines what developers who use these tools can achieve. And the other is the user interface, which makes this structure accessible, allows us to interact with it. And both these levels frame our intuition and our thought process when we design with this media. Now, you heard again and again today the criticism towards the boundary representation paradigm. All the software tools we have at the moment for design, they're using more or less the same kind of underlying representation. If I were to ask my students to design a hammer, I would get something like that. Maybe it would look much better, but the conceptualization of the hammer would be what is important about it is the actual exterior frame, the shape of the hammerhead. But in reality, if a blacksmith creates a hammer, what is important is the distribution of soft and hard iron within the hammerhead that absorbs vibrations so that you don't injure your hand when you use it. So the boundary representation basically assumes that there is a boundary that separates an interior from an exterior. And what happens within the boundary is not part of the thought process, part of the design process. It's very difficult to define and work with. It also affects the way we think about architecture because it very strongly suggests that architecture is about the design of envelopes or skins that, again, separate an interior with an exterior. I mean, there are ways to go around it, and conceptually, architects have been very innovative and creative in that sense. But in general, the tools we are using do strongly suggest this distinction. We also have, as you saw today, this is the most cliché image I could find, the bone structure, which is a functionally graded material, the porosity and the alignment of the fibers is responding to stresses and so on, all these wonderful things. But we would like to be able, as designers, to somehow define, manipulate, or at least take into account. So at the same time, the software tools that we are using, they are based on a vector representation when we are talking about CAD and design software, or in a raster representation when we talk about image editing software. But if we wanted to create these continuous material distributions, we need a new paradigm. And what we are suggesting is a hybrid between traditional CAD modeling and workflows from image analysis and the biomedical field. It's also part of my interest comes from my exposure to topology optimization. When I was working in an engineering firm, we did a lot of research and developed interfaces that implement these sort of methods. And in the opening chapter of Bedsoe's book on topology optimization, he mentions the problem of structure as one of a continuous material distribution, which again is a different paradigm in terms of how we think about structures, even if the forms are familiar. This kind of cantilever, you can find the optimal form in many different ways, and actually we know the optimal conditions and shape even without the topology optimization. But the way we reach that conclusion using these methods somehow suggests a different way of thinking about structure and materiality. So it's basically a more fuzzy object. So as obviously, again, we're going to talk a little bit about voxels as extensions to 2D pixels. These are very straightforward, you know all these things. Our software is based on a multi-channel voxel image that has two channels, one for designating shape, the distinction between void and solid, but in a continuous field, so you can select different isosurfaces, and at the same time, by using a gradient, you maintain some information about normals that allows a smooth reconstruction of the underlying shapes. And the secondary channel, which is the material mixing. And this comes from the fact that when we started the research, we were working with object, now stratasys, and they're now they're multi-material 3D printer Connex. So the way this achieves the continuum distribution of material is basically a mixing of two materials at variable ratios. So this secondary channel describes the mixing ratio between two materials. So if the material A is transparent and the material B is opaque, you have an opacity gradient. If one is rubber and the other is plastic, you have a stiffness gradient, and so on. So by combining these two channels, we have objects that define both the shape and the interior distribution of material. So first of all, these are use of the UI for monolith. So it's a user interface that allows you to define this kind of volumetric model. So you're working on a voxelized space. You can work with workflows that are familiar from using any kind of image editing software, but you can also apply filters on models like Gaussian blurs and so on that are workflows, again, that come from image editing. You can define formulas, parametric formulas that define the shape and superimpose them. Monolith is based on an idea of a parameterized stack of superimposed voxel images. So here creating one formula generated pattern, and then the gradient, the material mixing field, is another formula generated pattern. Again, operations like sweeping and lofting and all this becomes fuzzy and continuous. So here is lofting between two images that you can draw in any software. And you can achieve types of joints and continuity that are very difficult to do with surface modeling. And that is because voxel-based modeling is more flexible in how it handles topology. So you can have continuous topological variations that are difficult in the BREP regime. You can work and manipulate complex data sets and apply, again, transformations on them. There are visualization tools that allows you to see the inner structure. These are taken from the medical field and so on. You can also bring in information like meshes and voxelize it, like you see the bunny here. The bunny is a reference mesh. The voxelization, again, has to use traditional typographic techniques that create a little bit of anti-aliasing along the boundary so that it maintains information about the gradient and the surface. So you don't get a pixelated bunny. But you can also work on its interior. You can also define that I want this opaque material here and this transparent material there. You can apply filters like Gaussian blurring and so on. Boolean operations become fuzzy again because these are continuous gradient fields. They are not necessarily a black and white condition. And so when you combine gradient operations, you have this typical mixing of additive, subtractive, and so on. But there is a little bit of fuzziness, so it's a natural filleting that comes with this process. And this is another workflow, which is the equivalent of editing the control points of a surface, a grid-based NURB surface, but you can choose different interpolating schemes, and that changes the underlying shape. So by changing the weights of the control points to positive or negative and the interpolation scheme, you can very easily sculpt this sort of continuous objects. We can also do workflows. So we're trying to position it as a hybrid. So we do allow workflows that encompass software that we are already using. So it can have a live connection with Rhino, for example. So you can have the skeleton defining geometry from Rhino or Grasshopper directly imported or emitted towards Monolith. It can even work in real time. And there is a back and forth of translation between skeleton geometry, FREP, boundary representation. So there is workflows that combine all the familiar ways of working. The other important thing when you're working with voxels, though, is that you can apply filtering operations. And filtering is a concept that comes from image analysis. And that's an interesting transition point. If the software we are using now, the BREP software, was not developed for architects. It was developed for mechanical engineers. And the way it uses the assembly paradigm and the modeling system, it presupposes or implies a mechanical engineer's mindset. The voxel-based software is developed and comes from the biomedical industry. And the mindset there is one of filtering, signal analysis. So geometry is seen as a signal. It's not seen as discrete units, differential manifolds and so on, but it's seen as a signal that you can decompose and rearrange in many different ways. So as I said, you can do Gaussian blur, which means you transfer this object into its frequency space, cut off some frequencies, and bring it back into its configuration space. You can apply the blurring at different channels. So for example, we can smooth the shape channel without smoothing the material density channel. We can have highly nonlinear filters that actually drastically change the topology. These are shape modifiers that you cannot apply easily on mesh-based or BREP-based geometry. And different types of noise, and then all these techniques from medical images like dilation, erosion, and so on. But on top of that, we wanted to engage, because of the way multi-material 3D printers work, they actually don't directly chemically mix the materials. They're just creating dots, small micro patterns of different materials, and that is what we perceive macroscopically as an intermediate material. So, and that is, they are basically inkjet printers. And for that, we wanted to look into traditional typographic techniques, but extend them into 3 dimensions. So basically, there is a macroscopic field that is determining the overall shape. There is a microscopic field that has to do with the dots of ink or material and the intrinsic properties of this material. And there is a mesoscopic field that is up for grabs. It's a design problem there because it defines intermediate, elastic, and optical properties. So we looked a lot at techniques of dithering, error diffusion, half-tone sets of tools. So we can define our own patterns even in just in 2D. So this is just working in Photoshop, for example. You define some kind of skeletal pattern that you want to use as a 3-dimensional halftone. Then create some kind of shape that has some material gradation inside. This has a vertical gradient from material 1 to material 2. And bring this pattern as a micro pattern inside. Again, because we are using these visualization techniques that are based on GPU processing and come from medical imaging, we don't have to generate very heavy and difficult meshes. It's just visualized in real time on the GPU. So using 3-dimensional textures and so on. So it becomes possible to work to define both the detail, the micro pattern, and the microscopic shape almost in real time and at interactive rates. So you can intuitively start working with this sort of tools. So here you see a gyroid, the other cliché shape for 3D printing, with the gyroid as a micro pattern, but the term is the gradient. Again, the interaction is instantaneous. And you can also see the exact cross-sections that are sent to the printer in the end. So again, using these techniques, we had some workshops with students and combine it with other research areas and try to see what are the design opportunities in these systems. These are microscope images of some of the micro patterns. It's mostly dealing with optical, some with elastic properties. It's not only about material density, material 1 versus material 2 ratio, but also anisotropy of the material that we can micromanage. We can create things that look transparent from one view and become opaque from another, and we can manage the anisotropy of the optical properties throughout the material. We can create interesting transmission of light through the material bulk. And these are some design of students that have hidden designs within them. You can have patterns that align from a particular view and they let a lot of light through, but from other views become almost opaque or at least fuzzy. And also we are interested in research in when we have the ability to do elastic materials of nonlinear deformations. But this is from research with Katja Bertoldi's group in Harvard School of Engineering. So I cannot show the actual applications here because it's not published yet, but anyway. We can kind of combine soft and hard materials and create interesting secondary actuation. Again, by manipulating the anisotropy of the mixing of the soft and hard material, we can create surfaces or even volumes that bend in unexpected ways because it's, the grain of the material is actually designed, so it's not the grain that we get from an industrial process right now, which is always homogeneous, or from a natural process that is uncontrollable, but something that is a designed grain. The other power of voxel-based techniques is in analysis. Basically, voxel-based techniques are very appropriate for GPU processing, and a lot of near real-time analysis techniques are possible to implement. So because you already work on a discrete space, you don't have to have the complex discretization step that you always have when you try to analyze solid models. But you can directly apply finite element techniques on the analysis model, and especially static analysis is almost instantaneous. There are new techniques like lattice-Boltzmann simulations for fluid dynamics and similar techniques for heat transfer. So we can, for once, create a model that uses multi-physics and has a real-time feedback for the designer. Also, as I said, part of the inspiration came from a topology optimization, which, as it suggests, a change of paradigm from one of connecting and assembling elements to one of a distribution of material in space. So if you set the penalization factor in this topology optimization algorithm, if you force it to choose between black and white pixels, so in the end to have a solid and void structure, you get something like that. And this form, we know it from traditional engineering. It's very well known. The whole optimal truss-like distributions are very well known. But the interesting thing is that the optimal form is not this one, but it's this one, the one that has the continuity inside. If you try to remove the continuity of the material distribution, then you end up with the suboptimal form, actually. So the true optimal, the true minimum in the minimum compliance problem is actually a continuum form. It's not a discrete form. But usually with topology optimization, you get something like that, right? You 3D print it, and this is the final outcome, and it's a direct interpretation. Now in Monolith, we integrated the structural analysis and topology optimization system. You can set up the modulo of elasticity of the two materials that you are mixing, and you can set the curve of the mixing of moduli in relation to mixing of materials. Because something to keep in mind is that if you have material A and material B, and you mix them in a half and half ratio, you don't get half and half the modulus of elasticity. This is an active area of research, but actually we try to figure out what are the moduli of elasticity mixing curves, and as well for optics, the optical mixing curves for the materials. So here you can see tension compression diagrams in a typical topologically optimal truss, deflections. stresses, stress lines. So in a sense, we can actually directly fabricate this object. And what is this object? So it's not quite a truss, one category of traditional engineering, and it's not quite a reinforced beam. It's something between the two, and it's also a continuum. So it's a more or less a new type of structure that we can start thinking about. Because it has a continuous variation between the hard and the soft material, you avoid certain effects of concentration of stresses on material boundaries because it becomes a little bit more diffused. So it has a few advantages, and it's something that we are looking into at the moment. We can also, because we can control the printing in this very minute scale on the deposition of the different materials, we can create very fine line patterns without ever having to mesh anything, without having to create meshes with billions of triangles. We can directly print line patterns, and this is principal stress directions within a little slab volume. And this is another model that has, again, the full three-dimensional principal stress curve distribution within the bulk of the transparent material, which is an interesting opportunity because it's not, again, only about the density of the material, but the directionality at which you place one material versus another is extremely important. If, for example, you think of this as a reinforcement problem, these are the curves that you probably want your reinforcement to follow or to align to. So you can download Monolith on this address if you want to try it. But this hybrid approach to modeling that combines workflows from traditional CAD or assembly-based paradigms with workflows from medical imaging that are voxel-based and continuous, in a sense is pushing the scale space of which is accessible during the design process. So we're pushing what we mean by detailed design further down the scale, further to smaller and smaller scales. But also now the scale space is understood as a continuum. So it's not about we're doing the planning and then the detailed design and choosing materials, but potentially we can have this continuum scale space that we traverse during the design process. And scale is not anymore about the size of the designed object, the artifact, but about the information density. And I think I found the discussion about tectonics in the morning quite interesting, of what is the state of tectonics, but it seems that tectonics right now is this empty signifier. It's a signifier looking for a content, and this is a good indication that we are in a transitional period in terms of modes of production. Thank you.
We're going to have half an hour break, and then our last two speakers, followed by a discussion with Theo Spiropoulos.